Hello and welcome to the video series about unbounded operators. This is a video course in the field of functional analysis, and I would say it's already very special and advanced. Therefore, in order to understand this course in the best way, you should already have good knowledge in linear algebra and real analysis. And of course, you can always refresh your memory by watching my videos about these topics. And moreover, if you watch my functional analysis course, you already learn a lot about bounded operators. This means this course here expands the functional analysis course by so-called unbounded operators. Now indeed, it turns out that these operators are not easy to describe, but they occur a lot in applications. However, before I start with the motivation here, first I really want to thank all the nice people who support the channel on Steady that made this video course possible. Since this is such a special topic which will not generate many views on YouTube, I can only do it because of your support on Steady or Patreon. And as a thank you, you will always find the PDF versions and quizzes for the videos on my webpage. Okay, then let's start with the topic and let's clear up why unbounded operators are so important. In fact, we immediately have a mathematical reason, because when we deal with partial differential equations, we immediately see unbounded operators. So the whole theory about partial differential equations is much easier to understand when you know what unbounded operators are. And obviously, we will explain these connections in this course. Now, historically, the next one might be the biggest motivation after all, because you need unbounded operators to describe quantum mechanics. So you might already know that in this physical theory you need operators, so you definitely need functional analysis, but it turns out that you cannot avoid unbounded operators. Indeed, one needs two special objects as operators, and we call them x and p. So for example, for one particle, the one measures the position of the particle and the other operator measures the momentum of the particle. And now the physical reality tells us that the order of these two measurements matters. This means xp is different from px. And of course, by using functional analysis, we can describe this as a composition of operators. However, now the order of the composition matters in the sense that the difference is proportional to the identity operator. More precisely, we also have the imaginary unit here, but this is not the important part now. The crucial thing here is that we cannot satisfy this equation with just bounded operators. This means we have to extend the notion of a linear operator to do quantum mechanics. And in fact, we will see that with unbounded operators this works. However, together with the unbounded operators, we get other technical difficulties into the theory. And we will immediately see this with the first definition here. But let's first start with some objects we should already know. Namely, the first things we need are two normed spaces we call x and y. So we have two vector spaces over the same field, and they also carry a norm. And you might know we either have real vector spaces or complex ones. Therefore, if we call the field f, it's either the real number line or the complex plane. And I can already tell you, most of the time you can just think of complex vector spaces here. Okay, but now immediately something new arises, namely we need a domain for our operator. And this will be a subspace in X, and we call it D. Hence, now the map we consider and call T is a linear one. And you can put in elements from the subspace D and you get out elements from Y. And now in this course we keep it simple, such a linear map we always call an operator. So please keep that in mind, if we talk about unbounded operators, we implicitly mean linear operators. Okay, and now it's a good time to also talk about other notations people use to denote such an operator. Now the first one is very similar. Some people just use the subset relation here in the definition of the operator again. This makes sense because often the space X is the important normed space here. However, some other people abuse this notation a little bit by omitting the actual domain here. And if they are nice, they at least say somewhere that this T has the domain D. So you can recognize with this that some people see an operator as a pair of two things. First, they say they have an action defined by T and then a restriction to a domain D. So this keeps it very short, but you also often see that in some books. Or similarly, instead of a pair, one writes T with domain D. But instead of the word domain, one also often uses D of T. Okay, maybe that's good enough for the different notations you could stumble upon, but let's go back to the actual definition here. Now for this course, a very important term will be given by so-called densely defined operators. And you might already expect that these will be the operators we will discuss in the next videos. And the definition should be very clear. T is called densely defined if the domain D is dense. More precisely, this means if you take the closure in the space X, then you get the full space X out. So maybe the domain of the operator is not the whole space, but it's very close to that in this sense. And here please note, this thing is only interesting in infinite dimensions, because still D is a linear subspace. So only in infinite dimensions we could have smaller subspaces that are still dense in the whole space. Okay, by knowing that, we can also write down two important subspaces we use all the time. And of course, I mean range and kernel for the operator T. So the explicit definitions you might already know, but because we have to consider a domain here, I want to write them down. Now first, the range of T is given by all the elements we hit on the right hand side. This means we have to go through all lowercase x in D. And what we get is a subspace in Y. So please remember that, it's still a linear subspace. Okay, and now for the kernel, we have to take all the points x that are sent to 0. Therefore, what we get here is a linear subspace in X. Okay, and with that we have it. We have the range of the operator T and the kernel of T. And now in the next step, we can finally recall the definition of boundedness. And then, of course, if you know what bounded means, you also know what unbounded means. So now bounded means we find a constant C, which we can choose greater than 0, but it should be a finite number. And now for every point x in the domain, we can calculate Tx in the norm of y. And now this one should always be bounded by the constant c. More precisely, it's c times the norm of x in the space x. And here you should recognize, if you calculate the operator norm you have learned in the functional analysis course, you see this operator norm is bounded by the constant c. And therefore the operator T is called bounded. And now if the operator norm is infinite, we call the operator unbounded. Or more precisely, we can do the negation here, which means for all constants we find at least one point x, such that T of x in the norm is greater than c times x in the norm. This means the ratio Tx to x exceeds every bound. And therefore, the operator norm as a number would give infinity in this case. Indeed, this can definitely happen, and we will see some important examples in the next video. However, here I first want to recall an important equivalence from the functional analysis course. Namely, a linear map is bounded if and only if it's continuous at all the points in the domain. So you see, for operators, the terms boundedness and continuity are connected in this way. Therefore, unbounded operators, as we want to consider them in this course, are not continuous at all. Indeed, an unbounded operator has to be discontinuous at all points. So this is important to remember. Unbounded means not continuous at all. And there we see again, this is definitely something that can only happen in infinite dimensions. Of course, in finite dimensions, every linear map has to be a continuous map. However, in infinite dimensions, we have so many directions that the continuity property can fail. And at this point we already know we cannot ignore such operators because they occur in a lot of applications. And therefore I would say, let's look at some examples in the next video and let's discuss it more. So have a nice day and bye bye.